This is the Chapter 9 practice test walkthrough. Number 1. In this equation, which are the products? A plus B produces C. Things on the left-hand side of any equation are called the reactants. Okay, so A and B are the reactants here. And the stuff that comes after the arrow on the right-hand side are the products. In this case, there's only one product, which is C. The answer is B, but in the equation it's letter C. In a chemical equation, lowercase g in parentheses after one of the substances means that it is which of these? Produced from nothing, that doesn't happen. Dissolved in water is AQ, a solid is S, and G is a gas. So again, this is answer choice B for number 2. How many total atoms are there in 4 Fe2 SO4 3? So I like to work sort of from the inside out on this. So go into the parentheses first. Inside the parentheses you have 4 oxygens and 1 sulfur for a total of 5 atoms. Now those 5 atoms are multiplied by 3 on the outside, so that gives you a total of 15 in the parentheses, and then it's Fe2, so that's 2 more. So you have a total of 17 atoms in this compound, and then the coefficient of 4 means you multiply the whole thing by 4. So 4 times 17 is 68, which is answer choice D. What type of reaction involves one reactant and 2 or more products? So we're looking at something that looks like this. AB produces A plus B, and it could be ABC produces A plus B plus C. The key is one reactant, 2 or more products. That is always a sign that you have a decomposition reaction. Which type of reaction usually takes place in solutions and produces a solid, gas, or water? Well, decomposition, that's not what we're looking for. We're looking for double replacement. This is where you have AB plus, I'll say CD, and then your products are CB plus AD. Double replacement means that the 2 halves of the compounds trade place, and this usually takes place in a solution. Synthesis is 2 things becoming 1. Combustion is a combination with oxygen and some other substance. Number 6, what type of reaction is K plus Br2 produces 2KBr? That is the same formula as A plus B produces AB. That's going to be a synthesis reaction when you have 2 or more reactants and only 1 product. That's always a synthesis reaction. Which types of reactions can sometimes apply to the same question? Combustion and synthesis. Well, combustion in one form looks like A plus O2 produces AO, or AO2 if you want to balance it that way. Synthesis looks like A plus B produces AB. So sometimes the formula for a synthesis reaction and a combustion reaction can look the same. Which type of chemical reaction would this be classified as? So here, if you look, you've got Al with hydroxide on the left, H2 with sulfate on the left, and on the right you have aluminum with sulfate, and you have hydrogen with OH or H2O. So this is where you have 2 compounds that then trade halves, and that's always called a double replacement reaction. Identify the type of reaction shown by this equation. So here you have HgO produces Hg plus O2. That should really be a 2 and a 2 to balance it out. But here you have the same formula we were looking at earlier where you have one reactant becoming 2 products. That is a decomposition reaction. Which type of reaction is this an example of? This is another case where you have iron and potassium trading places with each other. Both are in compounds on both sides of the equation, which makes it a double replacement. If iron was by itself and potassium was in a compound, and then potassium was by itself and iron was in a compound, that would be single replacement. You're not combining with oxygen here, it's not combustion, and you've got more than one product, so it can't be synthesis. What type of chemical reaction is this? Here you have aluminum as an element by itself. Iron is part of a compound on the left. On the right, you've got iron by itself, and aluminum has moved into the compound. That is the case for a single replacement where you've got one element and one compound on each side, and the element that's by itself has traded places with one of the elements in the compound. What type of reaction takes place when propane reacts with oxygen to produce carbon dioxide and water? Well, if you wrote this out, it would look like this. The key is anytime you have something reacting with oxygen, you're looking at a combustion reaction. Sometimes, again, that can also be a synthesis reaction, but in this case it produces carbon dioxide and water. That "and" means there's more than one product, so it couldn't be synthesis. That wasn't a choice anyway, but just to keep in mind, sometimes a combustion reaction can also be a synthesis reaction. Okay, we're going to balance this equation. First thing to do is take an inventory. We've got 4 phosphorus and 2 oxygens here. On the right we have 2 phosphorus and 5 oxygens. Okay, so we've got an odd number on the right for oxygen, we've got an even number on the left. That number is never going to be odd, so we have to look at making this one on the right even. Well, the easiest thing to do here would be to double that, which gives us then 10 oxygens. It also doubles the number of phosphorus we have. So conveniently that balances the phosphorus, and now we just have to fix the oxygen on the left. If we put a 5 in front of the O2, that gives us 10 on the left and 10 on the right. So the equation is P4 plus 5 O2 produces 2 PO2 O5s. Okay, let's take a look at this. We've got hydrogen. There's one there and one there for a total of 2. NO3, anytime you have a polyatomic ion, you want to look to see if maybe you've got the same polyatomic ion on both sides, because if you do, you can kind of keep it together for tracking. So I'm going to say that that's 1 NO3 instead of 1 nitrogen and 3 oxygen. And then I've got 1 sodium, and I've got the other hydrogen we already counted. Then I've got CO3, but I don't have CO3 on this side, so I have to break up the carbon and the oxygen. Okay, now I'm going to count the right-hand side. I'm going to go in the same order. So hydrogen over here, there's H2, and it doesn't appear anywhere else. So that's 2. NO3, like I said, that's together on the right as well as the left, so I'm going to keep it together. That's 1. There's 1 sodium there. There's 1 carbon here. And then oxygen, there's O2 plus another O for H2O, and that's 3 oxygens. So it's already a balanced equation. You don't actually have to do anything to that. It's already balanced. C7H16 plus O2 produces CO2 and H2O. This is combustion reaction again. To tally up, I've got 7 carbons, 16 hydrogens, and 2 oxygens on the left. So 7, 16, 2. Those are pretty easy numbers to work out. On the right, I've only got 1 carbon here. I've got 2 hydrogens here, and I've got 2 oxygens there and another one here. That's 3. Oops, sorry, 2 hydrogens, 3 oxygens. Okay, so I'm going to go ahead and start. Remember, if you've got oxygen by itself, save it to last, because a lot of times you can kind of go back and fix things at the end with an element that's by itself. So I'm just going to start at the top and work my way down. I've got 7 carbons on the left and only 1 on the right. So if I multiply CO2 by 7, that gives me my 7 carbons on the left. Does change the number of oxygens though, because the 7 times O2 means I've now got 14 oxygens in this molecule, and I've got another one here, so that's 15 oxygens. Now I'm going to go down to the next one, hydrogen 16, hydrogen 2. If I put an 8 in front of the H2O, that would give me 2 times 8, 16 hydrogens. It also again multiplies this oxygen in the H2O times 8, plus I said I had 14 over here in CO2, so 14 plus 8. Okay, now I've got 22 oxygens. So then if I go back to the right-hand side, I've got O2. I need to be 22, so if I multiply the O2 by 11, there's my 22. So your coefficient should be 1 here, as we don't write it, and then 11, 7, and 8. That balances out the equation. Aqueous sulfuric acid, and there's a typo here. Sulfuric acid is not H3PO4, it's H2SO4. Yield aqueous aluminum sulfate and water. So H2SO4 aqueous plus aqueous aluminum hydroxide. Aluminum is a +3 ion, cation, so you need 3 hydroxides to balance that out. That's aqueous. The products are going to be aluminum sulfate. Now sulfate is a -2 polyatomic ion, aluminum is a +3. So I need 2 aluminums for a total charge of +6, and I need 3 sulfates. Now I need to check on my solubility chart. Sulfate is soluble with anything except the generally the alkali earth metals. So that's going to be aqueous still. And then water is liquid. So, okay, use the activity series to determine if these reactions will take place. If they do not, write NR for no reaction. If they do, make sure they're balanced. All right, magnesium, solid magnesium, and aqueous zinc nitrate. Well, let's take a look. Magnesium is here on the activity series, and zinc is about 3 spots down. So the magnesium, which is by itself, is higher on the activity series than zinc, which means a reaction will take place. So we start with solid magnesium plus zinc nitrate aqueous. The zinc and the nitrate, the zinc and the magnesium are going to trade places, which means you end up with zinc solid by itself and magnesium nitrate, and it just so happens that the charges all balance out. So the equation is already balanced. You don't need to put any coefficients in there. Iron plus lead nitrate. Okay, iron is not, it's kind of right in the middle of the activity series, but lead is even lower down. So iron is more reactive, which means you do have a reaction. So they're going to trade places. And we're going to assume, based on the activity series also here, that we're talking about iron 2. So again, this is lead 2. You can tell because there's 2 nitrates, and each nitrate is -1. So just switch out the metals. You don't need to change the number of nitrates. And, I'm sorry, that should be a 2. You don't need to change the number of nitrates. Copper reacts with iron sulfate. So let's find copper on the chart. It's down near the bottom. And iron, as we've seen before, is kind of in the middle of the chart. So iron is above copper, which means iron is more reactive than copper. So copper cannot replace iron in this compound. So there is no reaction. NR can't happen. Chlorine and iodine, sodium iodide. With the halogens, they're not on this list, but the higher up the periodic table they are, the more reactive they are. So chlorine is above iodine in the group of the halogens. So chlorine will replace iodide, which means that they'll trade places. So it goes from chlorine gas and sodium iodide in solution, aqueous, and then the chlorine and the iodine trade places. So you end up with iodine gas, which is I2, and sodium chloride. And then to balance the equation, we need 2 sodium iodides and 2 sodium chlorides to balance that out, and the sodium chloride is aqueous. Okay, aluminum sulfate is used in water treatment because aluminum is reactive, which means that it will react with a lot of the impurities that are in the water. It also forms solid precipitates many times when it reacts with other impurities in the water. So the aluminum will react with a lot of things, and it will also form solids, which you can then filter out of the water. So you're looking for something that's reactive, that forms precipitates that can then be removed, and if reactivity was not a factor, it's kind of not the best way to word the question, but what other metal would be the best choice? Well, if you're looking for something that's really reactive, it would be the top of the list, like lithium and sodium. Of course, those will also react with the water itself, and you can't have that. But the point is, you're looking for something reactive that will form precipitates that can be filtered out. So depending on the application you're looking at, you sometimes want metals that are more reactive, or metals that are less reactive if you're looking for something that would end up being more durable, which is why things like copper, silver, gold, and platinum are used in jewelry and coins, which are supposed to last a long time, whereas other things are used less often. Okay, products of the reaction balance the equations and show the state. So here we have iron chloride and sodium hydroxide, and they are going to trade places in the solution. So iron chloride, when it's aqueous, and sodium hydroxide are aqueous in solution. When you mix those together, the sodium and the iron are going to swap places. So you're going to end up with sodium chloride, which is always going to be aqueous, and iron hydroxide, and you need to check the chart to find out if the iron hydroxide is soluble or not. And if you look on the chart, you'll find that hydroxide, when it combines with iron 2, and we know it's iron 2 because it's combined with 2 chlorides, it forms a solid precipitate. So then to balance the equation, we have 1 sodium on either side, we have 2 chlorines on either side. So we need to put a 2 in front of that, which gives us 2 sodiums. So we need to go back over to the left-hand side to balance the sodiums, which gives us 2 sodiums and 2 hydroxides. Now on the right-hand side, we happen to have 2 hydroxides, so that's all now balanced out. So FeCl2 plus 2NaOH yields 2NaCl plus FeOH2, solid. Aqueous sodium chloride plus aqueous silver nitrate. So sodium chloride is always NaCl, it's always aqueous. Silver nitrate is one of the few silver compounds that is soluble in water. Anything with nitrate is soluble in water. So if we swap the silver and the silver goes to the chloride and the sodium goes to the nitrate. So check your solubility chart again. You'll see that sodium and chloride, sodium is soluble with everything. Nitrate is soluble with everything. So sodium nitrate is certainly going to be soluble. It's going to be aqueous. Silver chloride is soluble with a lot of things. Silver is not one of them. So that's going to form a precipitate, solid. Okay, and now looking at the equation, everything's all balanced out. It's one of everything. We're going to write the chemical equation, the complete ionic equation, the net ionic for this reaction. So we got a double replacement. First we have to figure out what the products are going to be. So we have silver and potassium that are going to trade places. So we'll start out with the products being potassium nitrate, and if we want to write the whole equation out, we'll start with the reactants and then rewrite the equation. So silver nitrate, which is aqueous, reacts with potassium phosphate, which is also aqueous, and the products are going to be the reverse. We're going to have potassium nitrate, because the K in the silver, the K in the Ag trade places. So potassium nitrate, anything with nitrate is going to be aqueous. We'll come back to that in a second. And then the other is going to be AgPO4, and silver is a +1, phosphate is a -3, so you need 3 silvers there. To look at the chart, again, potassium nitrate, potassium is soluble with pretty much everything, nitrate soluble with pretty much everything. So to balance it out, you've got 3 phosphates on the left, put a 3 in front of it on the right, that gives you 3 phosphates and 3 nitrates. So if I put a 3 in front of the silver nitrate on the left, that gives me my 3 nitrates on both sides. Also gives me 3 silvers on both sides, which I needed to balance out the phosphate. We need to add the states, which is going to be aqueous for the for the potassium nitrate, and then silver. Like I said before, silver doesn't form soluble compounds with many things, so silver phosphate is going to be soluble. Now the complete soluble. It's going to be solid. The complete ionic equation. We rewrite the chemical equation, but we break up all of the ions that are aqueous. So 3 silver ions plus 3 nitrate ions plus 3 potassium ions plus 1 phosphate ion. That's everything that we have on the left-hand side of the equation above. All those are aqueous, and the products are 3 potassium ions and 3 nitrate ions. Those are both aqueous still, soluble. And then we have the silver 3 phosphate, which is solid. That's your precipitate. So for the net ionic equation, the key is anything that doesn't change from left to right, get rid of it. Those are called spectator ions. So the nitrate and the potassium are the same on both sides. They don't do anything. They're not part of the reaction, really. So we leave them out. So we're going to just put down the stuff that changes. The 3 silver ions, which are aqueous on the left, and the 1-phosphate ion, which is aqueous on the left, those two things combine to form the silver phosphate solid on the right-hand side. So that's the only thing that changes. That is your net result, your net ionic equation. Oldies but goodies, how many milligrams are in 5.69 kilograms? All right, so this is going to be a two-step conversion. Always start with the thing you're given. Okay, we're given 5.69 kilograms, so that goes on the top left, and we're going to have a sort of the railroad tracks here. 5.69 goes over 1 kilogram on the bottom. 1 kilogram is equal to 1,000 grams. Grams go on the bottom next. Milligrams that we're going to on the top. 1 milligram is 0.001 grams. Okay, if you multiply across the top and then divide by everything on the bottom, you end up with 5,690,000, and the unit here is milligrams. Electron configuration for sulfur. The significant figures, they're all set because those are all placeholder zeros. Sulfur is element number 16, so 1s2, 2s2, 2p6, that's 10. 3s2 gives me 12. 3p could hold 6, but I only need 4 to get to 16 electrons altogether. And finally, multiply these two numbers together and then round to the correct number of significant figures. So if you do this math out, 3.05 times 0.04620, the full answer is 0.14091. But look at the equation. This number has 3 significant figures, so our answer cannot have more than 3. Our current answer has 5, so we need to round off. So we go 1, 2, 3. I'm going to round it there. And the next digit, okay, since the next digit is a 9, I'm going to round it to 0.141.